Hi, welcome to videos on rectifiers and filters. So this is part 3. So in this video we shall see the simulation and the working of full wave rectifier with C filter. So we know that this is a full wave rectifier with a capacitor filter. So let us consider case 1 when D1 is on and D2 is off. So D1 on is represented by a voltage source and a forward resistance RF1, and D2 off, which is this D2 when it is off, is represented by uh, the reverse resistance RR2. So since diode D1 is on, the capacitor C is charging through the diode D1, having a time constant, having the charging time constant tau charge as RF1 into C. So let us see the case 2 where we have the D1 off, now D2 is on. When D2 is on, now you can see the capacitor is charging again through diode D2 having a forward resistance of RF2 and the capacitance C. The charging time constant tau CH2 happens to be RF2 and RF2 into C. So we're going to also have a third case when both the diodes are off. When both the diodes are off, you can see now both the diodes are represented by the reverse resistance RR1 and RR2. Now capacitor starts discharging through this resistor, load resistor R. The discharge time constant happens to be R into C. So we have three cases in case of full wave rectifier when only one diode D1 is on, D2 is off. Second case D1 is off and D2 is on. The third case is when both D1 and D2 are off. I can see this is how the waveform will look like. So this is when t is equal to 0. So when the input voltage is less than Vd on, so both D1 and D2 are off. So that's why capacitor is not at all charged. So assuming that initially capacitor is not charged, so it remains in 0. So once D1 turns on and D2 is off, now you can see capacitor is charging with a charging time constant of RF1 into C. So it goes till the peak, where peak is Vp minus Vd on. You can see now this is the difference between the input and the output, which is a difference of Vd on. Once both the diodes are off, I can say since it is in positive half cycle, D2 is off. Now since the capacitor voltage is more compared to the input voltage, now it starts discharging through the time constant. The capacitor discharges to ground through the resistor R having a time constant that is R into the resistor R and the capacitance C. So as you can see here, so it is discharging through resistor R. So the time constant is R into C. So that's what is happening when both the diodes D1 and D2 are off. So this will be keep on discharging as long as the both diodes are off. Now once again diode D2 turns on, now the capacitor is now charging. It goes till the peak. Now both the diodes are off. It is now discharging. Now what is keen to observe here is, so when the capacitor is charging, it is charging almost instantaneously along with you can see the shape is almost sinusoidal. While discharging, it is exponential nature. I can see it is coming down, whose time constant is decided by the capacitance C and the load resistor R. So let us see the simulation of the same full wave rectifier, and we try to analyze the circuit. Now this is the full wave rectifier. We can see there is a capacitance. So now this is we have put a resistance of 100 ohm, and you can also increase the resistance to a larger value, and you can see, so if I make it 1000 ohms, now you can see the amount of discharge happens to be very less. I can see it is not at all discharging to a greater value. It's almost staying there because the time constant is the charging time constant is very small. It charges almost instantaneously, so it is not at all discharging because the resistance value is too high. So what I can do is, if you want to discharge to a larger value, so you may have to either reduce the resistance value or the capacitance value. So let me just reduce the resistance value to around 500 ohms and try to see what happens to the ripple voltage. Now I can see now the discharge, it is now discharged to a more value, so the ripple voltage is more now. So we can find the expression for the ripple voltage, which we'll be deriving in the coming class, which will be given by Vp minus Vd by 2FRC. Now you can clearly make out one difference between the ripple voltage of the full wave rectifier and half wave rectifier. If you go back to half wave rectifier, in the previous video we have seen that the ripple voltage is given by Vp minus Vd divided by FRC. So in the denominator we have FRC, whereas in case of full wave rectifier, the ripple voltage is actually reduced by half. I can say it is numerator remains to be same, Vp minus Vd, but the denominator is increased by 2 times. So naturally the ripple voltage for a full wave rectifier with same values of R and C and the frequency happens to be half compared to the half wave rectifier. This is the 2. You can actually make out the value of 2, okay, how it is coming. So in the class we'll discuss, okay, how does this ripple voltage will reduce in case of full wave rectifier. And this is a bridge rectifier with C filter. What I request all of you is that you already know the bridge rectifier circuit. We have seen the rectification, and I request you to write the circuit diagram of a bridge rectifier with C filter. The only thing is that you are supposed to put a capacitor C across that load resistor R, and you can certainly draw the charging and discharging waveform as it is shown here. The only difference in case of a bridge rectifier, it will be almost similar to this type of shape. Only difference is this peak voltage will not be Vp minus Vd on, it will be actually Vp minus 2 Vd on. So there is a term 2 will be get added to this Vd on, because we're going to have 2 diodes conducting simultaneously when the capacitor is charging. So capacitor will charge up to Vp minus 2 Vd on. So that is a major difference. So since the peak voltage is Vp minus 2 Vd on, the ripple voltage changes to Vp minus 2 Vd on divided by 2FRC. So the denominator remains the same, only the numerator reduces to Vp minus 2 Vd on. So naturally the difference between Vp minus Vd on and Vp minus 2 Vd on is not too much. The ripple voltage of both full wave rectifier and the bridge happens to be almost the same for given set of values. And you can certainly write the waveforms, and then, so this is a single word waveform, it's not a wave and form, so let me just correct it. So let me make it as waveform. So this is not from, this is waveform. Let me make it waveform. Now this is waveform. I don't care how I made it. Okay, this is a waveform, and expression for the ripple voltage. The expression for the ripple voltage happens to be a slight difference compared to the full wave rectifier. It happens to be Vp minus 2 Vd on by 2FRC. So I want all of you to verify the ripple voltage whatever you're getting. Suppose if you want to verify the ripple voltage, what you can do is you can have 2 cursors on this. You can see now this is the maximum of the ripple voltage, and this is the minimum of the ripple voltage. Now the difference between this happens to be 314 millivolts. So this is what is ripple voltage. So this should be equal to this, that is 9.24 divided by 2FRC. So 9.24 happens to be Vp minus Vd on divided by 2 into frequency is 50 hertz multiplied by the value of R and C. So that should result in 314. I request all of you to verify this 314 should be equal to this expression, whatever you have here. So should be equal to Vp minus Vd on by 2FRC. 2 is a constant, F is the frequency, R is the resistance, C is the capacitance value, Vp minus Vd on is the peak voltage of the output. which is represented over here. So this is the peak voltage, which happens to be in this case 9.24 volt, and the value of F is 50. C value happens to be, you can just have a look at it. C value is 500 microfarad, and the value of R is 500 ohms. So I want you to verify this 314, is it close to that equation or not. So we shall do the simulations when you come back to lab.